All right. Welcome back, guys. All right, so this is gonna be your last lab assignment for those who could not attend the lab. Right. So before you start your doing your assignment, I need to tell you that this content over here is not fully covered yet. So this contents over here will be covered in your last week's lecture. I'm trying to push a little bit faster because the content we are covering over here in in this experiment will take more than a week. So that's why I'm trying to push the other content a little bit faster. Anyway, so in your introduction, you have three sections, and then we don't actually cover number one anymore, so you don't have to worry about the first one, and you will just need to focus on number two and number three over here. Right. So since we are dealing with physical quantity, please make sure that you read everything before you commence your lab assignment, because we need to use the equations given over here, as well as okay, it's not over here. Right, so once we find out heat in joules or kilojoule, you need to use the number of moles, and then you need to find out changes in enthalpy, which will be your Q value over number of moles. And then it will give you a certain number in joules or kilojoules per mole. Right? So these equations are given in your lab book or lab assignment file, and you should be able to find the relevant equations you need to use. And then make sure that you read these one carefully. Otherwise, you will get this one completely wrong, because we are dealing with a large number in kilojoules rather than joules. Right. And then we have an example over here, which is relevant to your lab task. Okay, so pre-lab quiz, have a look at each question carefully and answer the question carefully. Once you complete these questions, and then finish your lab assignment questions, and then come back here and have a look at these ones again. You might be able to find something not correct. Right. So this is an experimental procedure. So in part A, you're gonna dissolve sodium hydroxide sample, I would say pellet, into water. And when they dissolve or the sodium hydroxide dissociates, it will generate heat, right? And then we are measuring the changes in heat to calculate. We are measuring the changes in temperature to calculate the heat from the reaction. So that is what you need to do, and then the number you need are given over here. So mass over here is over here, mass of your water, and then your initial temperature is also given as well. And then when you follow the instruction, so today the first task is to find out temperature maximum or temperature final, right? So since we are trying to find out temperature maximum, you don't have to worry about this one, your maximum temperature, either at 720 second or 780 second will be your final temperature, right? And then eventually the heat goes down once it reaches the maximum. Okay, and then okay, looks like answer is already given. I will need to go through everything here again, but let's have a look how we get to these ones. So your mass of vial plus sodium hydroxide is 12.01 gram, and then mass of vial is 4.89 grams. So since we are looking for mass of sodium hydroxide, you need to do some simple calculation. So it'll be total mass minus mass of vial. So answer will be 7.12 gram. That's gonna be your mass of your sodium hydroxide, and then from mass you'll need to find out number of moles of your sodium hydroxide. So when it comes to say a pure chemical or pure compound or pure atoms or pure say molecules, you need to in solid you need to use mass over molar mass. So mass is already calculated here. And then molar mass of your sodium hydroxide is 40 grams per mole. So when you divide this one by your molar mass of sodium hydroxide, it will give you the number of moles, which is at 0.178. And then, so the next one will be calculate the heat gained by the water in the color metal. And then you will need to specify the unit, right? And then specific heat and mass. So using the equation over here, you need to find out a specific, you need to use the specific heat, which is given over here. So in this case, we're gonna use a specific heat of water. And the mass will be your total mass, because when you mix, when you put your sodium hydroxide in water, the reaction happens. So and then the heat goes from your heat comes from your dissociation of sodium hydroxide, but it disperses into the entire system, which is sodium hydroxide plus water. So mass should be the total mass over here, and then changes in temperature should be T final minus T initial, or T2 minus T1, right? So by using these numbers given and then number from your experiment, and then C will be 4.184 times by total mass, then it should be times, not plus, times by changes in temperature in Kelvin. You should be able to get 7,301.8 joule. So since we are dealing with a large number over here, we are gonna use just kilojoule. So instead of using 7,300, you're gonna use 7.3 kilojoules, right? That is the answer in joules. But if you still want to use in joules, keep using this number, but you need to specify your unit. Then next one is asking you to calculate the heat released from the dissociation or dissolution of 1 mole of sodium hydroxide. So you just need to find out the changes in enthalpy using the heat from your previous calculation, which is over here, and then actual number of moles. So since we did not have exactly 1 mole of sodium hydroxide, we will need to use the number of moles from your calculation, which is right over here, right? So using the equation over here, and then using the value from your previous calculation, the changes in enthalpy should be 7.3 kilojoules divided by 0.178 mole. And then once you finish calculating your numbers, you will have some numbers end up with kilojoules or more if you use kilojoules. If you use the joules, the number will be much bigger than whatever you are seeing. And then since this is an exothermic process, by convention, the sign of delta H will be negative. So instead of leaving your result over here as it is, you just need to put negative sign. And then 4.1 kilojoules per mole. Right? So this is a final result you should get from your first one. If your number is not close to this one, you made a mistake somewhere. So please have a look at your calculation again. And then part B. So we do have two separate experiments for part B. So B1 and B2. So they are exactly same reaction, but instead of using one specific acid and one specific base, we're gonna use two different types of acids and base, right? And then we're gonna compare the differences in B1 and B2. Right. So the number you will need to have is a molarity, which is specified on the label from your stock bottle. Since you haven't attended the lab, the number is already given. So molarity of your hydrochloric acid is 0.6, and the molarity of sodium hydroxide solution, not the solid, same as the one we did in A. So this time it is an aqueous solution. And then concentration is given at 0.5 moles per liter. And then mass is something you need to measure. And since you could not measure the numbers given, about 75 grams of each, which is same as 74.99 milliliters. Because the density of water is from here to here, I use the density of water. I think there's a specific term or number given over here. No? Okay, so it is not given. There we go. We need to assume the density of the stock solutions are equal to water, right? So it is 1 gram of water equals 1 mil, right? Because of that, if you have, say, 74 or 75 grams, it will be 74 or 75 mils. So from mass to volume is about same number, but different in unit, 0.99 ml. But the next one is provide units of the next next row is already provided in liter. So that is why you need to convert your mils to liter straight, ended up with 0.07499. And then same as over here. So using the volume and then molarity, you should be able to calculate number of moles. So since we are dealing with a solution, in this case, you will need to use concentration times volume in liters. Otherwise, you are putting your, if you use mass over molar mass, you are putting the mass of your chemical plus mass of your solid, which is water. If you do that, your number will be really big, and then your number will be not correct. Anyway, so using the number over here, so mole is concentration times volume, right? So concentration is given as 0.6 moles per liter times your volume in liter. So when you do it, your number of moles will be 0.045. And then we do the same for the sodium hydroxide solution, not the pellets or solid chemical. So when you multiply your concentration moles per liter times, will give you number of moles, which is already calculated. And then your initial temperature of each solution before you mix, because once you mix, you won't be able to take your initial temperature. We need to take the temperature of each one separately, and then you need to average these two for your initial temperature. So since they are the same, your average should be exactly the same as one of them. So it should be 25.05, and your final temperature was 28.11. And then total mass of solution, you just need to add these ones together, right? To find the total mass. So total mass is 74.99 plus 74.99, ended up with 149.98 grams of your total solution. Okay, so to calculate heat from your reaction, you will still need to use the same formula you used before. Heat capacity of water times by your total mass, heat capacity, mass, and then change in temperature in Kelvin scale, right? And then using the value from each calculation, you should be able to get 1.92 kilojoules. Before I move on to next one, if you are not sure why we are still using the degree in Celsius instead of Kelvin, the reason is that changes in Kelvin scale equals in degree Celsius scale. If you're not do it in Kelvin, you need to convert each one before you do any more calculation. So for example, let's just use the value over here, 28.11 plus 273 minus 25.05 plus 273 Kelvin. Right? So as you can see, changes in Kelvin and changes in degree Celsius are the same, because the minimal division of Kelvin and then degree Celsius scales are the same, right? Anyway, so using the value from your Q, and then you'll need to calculate changes in enthalpy. So in this case, you need to use the Q divided by number of moles. And then as you can see over here, we use the number of moles of the sodium hydroxide. The reason is that if there's no more reaction, there'll be no more heat coming from the reaction, right? And then you'll need to use the number of moles of your limiting reagent. In this case, limiting reagent is sodium hydroxide. So instead of using number of moles of your hydrochloric acid, we need to use number of moles of the limiting reagent, which is sodium hydroxide. So in the end, you have a value over here, and then you need to put negative value because it's an exothermic reaction. Your final is higher than your initial, right? Okay, so B2 is also pretty much same process. So instead of using the instead of using hydrochloric acid and then sodium hydroxide, in this case we use nitric acid and then potassium hydroxide. And the mass is given over here. And then using the mass, you need to convert this one into volume, which is already written over here. And then number of moles, you should be able to calculate using the equation. N equals C times V, right? and concentration is already given here, and the volume is the one you find out using the mass, right? And you do the same for the sodium hydroxide. So in the end, you have number of moles of your nitric acid and the number of moles of your potassium hydroxide. And then your initial temperature of each one is identical. So your temperature initial temperature should be 24.98 degrees Celsius. And then your final temperature is 27.99. And then again, total mass is mass of your total mass of your two different solution. So you should be able to calculate with no trouble. And then for heat, you do the same as P1. C is already given at provided at 4.184 times by total mass, and then changes in temperature in Kelvin scale. So in the end, you should get a specific value, and so in kilojoules, 1.888 kilojoules. Right. All right. So you do the same for the changes in enthalpy. So you use the Q value from your calculation over here, and then you need to use the number of moles of your limiting reagent. Same again, since we used pretty much the same amount of base and acids, and then since the concentration of base is lower than acid, this should be your limiting reagent, which is obviously smaller in terms of number of moles, which is much smaller than acid, right? So using the value from your Q and then number of moles of your limiting reagent, you will get about 51 kilojoules per mole. Obviously, you need to put negative sign because it's an exothermic reaction. Right, so number 2 is asking full equations and ionic equation for reaction P1 and P2. So full equation should be quite straightforward, right? You just need to put whatever you mix with, and it does not say full ionic and net ionic equation. Anyway, so full equation should be HCl, which is aqueous, plus NaOH, which is also aqueous, goes into NaCl, aqueous, plus water, which is liquid. And then when it comes to full ionic equation, you'll need to write everything down in ionic form. So from HCl, you should be able to write H plus plus the Cl minus. And then sodium hydroxide aqueous solution, it should be Na plus plus OH minus, right? And then once the reaction is complete, you should have salt water, right? Because of that, because it's a salt water, so still sodium hydroxide is in aqueous solution, should be Na plus plus Cl minus plus water. And then net ionic equation over here should be one without any spectators. So you just need to cancel the same ones. So for B1, you can cancel Cl minus as well as Na plus. So net ionic equation will be acid base making water. And then changes in enthalpy was about minus 51 kilojoules per mole. Right? And then for B2, since we don't have a full equation, we just need to write it down. We started with nitric acid aqueous solution plus potassium hydroxide aqueous goes into potassium nitrate aqueous solution plus water. And then for full ionic equation, you'll need to write everything over here into ionic form. So H plus NO3 minus from nitric acid plus K plus OH minus from your base, which is potassium hydroxide. And then since potassium hydroxide is still in aqueous, it will be K plus NO3 minus plus water. For net ionic equation, you just need to cancel the spectators, which are nitrate plus K plus, right? So net ionic equation should be same as P1, and then changes in enthalpy should be about minus 51 kilojoules per mole. Let's have a look at actual number. So, yep, so it was minus 51.205 kilojoules per mole. And then second one was minus 50 plus 881 kilojoules per mole. So when you look at these two numbers, they are quite similar, right? They are not exactly identical, but they are close enough to call it the same. All right. So let's have a look at the last one. So in this case, the reaction, not reaction C, reaction C or part C, whichever you want to call it. It is pretty much the same process as A and B, but we are combining reaction A and B into one reaction. That's what it is. So we start from sodium hydroxide pellets, and then we are putting this one into, not water this time, we are putting this one into HCl solution, right? Creating water plus Na plus. And so the process should be quite similar to the previous two, but you gotta be careful whether when it comes to calculation of the number of moles, you'll need to find out whether the chemical you are handling is in aqueous solution or the solid chemical, right? So the molarity is already given at 0.6, which is just the same acid for your part B. And the initial temperature is given at 23.58 or 58 degrees Celsius. And then mass of HCl solution is 145.59 grams. And then by mixing this one plus your sodium hydroxide, you created this much heat, right? Since we are handling solid NaOH, we are doing the same process. We took the meso vial plus NaOH, and then we took the meso vial later on. And then the mass of NaOH should be mass of everything, which is 4.1195 minus mass of the empty vial. So once you finish calculating this one, you will have 3.0145 grams. And then since you need to calculate number of moles, and then since we handled solid sodium hydroxide, you gotta use mass over molar mass to find the number of moles. So number of moles is calculated at 0.0754, right? Okay, so for it should be capital Q, not small q, is heat capacity of water times by total mass, because you need to mix these together to start the reaction, and then once reaction started, the heat goes into the entire system. The mass should be everything. So that one times by this one times by changes in temperature. So that should be from 34.75 minus 23.58 or 58. So anyway, once you finish calculating Q, you should have about 6.945 kilojoules. This is in joules, but I just straightly converting to kilojoules. And then for the enthalpy, you'll need to use the Q from your calculation, and then number of moles of your limiting reagent. So when you calculate the number of moles of your acid, it will be much larger than this one. When you look at part B1, right, about the 75 grams, you have 0.054 moles. Once you double the amount of your solution, your number of moles should be double. So it should be about 0.09 moles of HCl. So since number of moles of your sodium hydroxide is smaller than number of moles of hydrochloric acid, you will need to use the number of moles of your sodium hydroxide. Because we know that this is already smaller than this one, we didn't bother ask you to calculate the number of moles of your acid. Anyway, I just wanted to show you why we use this one again. Anyway, so once you finish calculating this one, you should end it up with about minus 92 kilojoules per mole. Right? Okay, so your calculation is done, and then you will need to write some conclusions. Okay, so it is asking you to write net ion equation of each one. So since B1 and B2, they are already covered over there, I'm not going to write it over here. Or maybe I can just write H plus OH minus goes into water. So it'll be the same, right? And then for the first one, your initial starting materials were sodium hydroxide pellets, which is in solid, in water. But when you mix, you should be able to see changes, right? Since it will be dissolved, you will see aqueous sodium hydroxide solution. So since we need to calculate spectators, which are water, your net ion equation will be this one and then this one. And then our changes in enthalpy was about minus 41 kilojoules. And then P1 and P2 we already did. So P2 should be same as P1. And then the values are quite similar or extremely similar with minus 51 kilojoules per mole. Okay, so last one was sodium hydroxide solid, which was same as A, but instead of water, we used hydrochloric acid aqueous solution, so it should be H plus the Cl minus, right? So once you put it in, so when you look at this one over here, once you put this one into aqueous solution, it will turn into Na plus OH minus, right? And then when you look at this one here, it's an acid-base reaction, right? Same as P1 and or P1 or P2, right? So it will create water plus Na, and then chlorine should be a spectator, right? So in the end, your answer should look like this. All right, so you need to compare the results of B1 and B2. What conclusion can you make? So when you look at the results of B1 and B2, although you use different types of acid and base, what happened within the reactions are the same, right? It's a simple acid-base reaction making water. Because of that, your changes in enthalpy are the same, right? Well, based on the number over here and based on what you see in your net ion equation, that's the only conclusion you can make, and which is obviously correct. Okay, so compare the results of C to those of A1 and B1 or B2, because B1 and B2 are the same. And I'll just say B to make it simple. What conclusion can you make? So I drew a simple diagram. So when you look at the net ion equation, right? Reaction C is reaction A and B in one reaction. Because of that, when you compare the changes in enthalpy of each one, it'll be pretty much the same, right? So enthalpy from reaction C was minus 92, and then from A was minus 41, then from B was minus 51, right? So in the end, so I'm not sure why we have these numbers over here. 41 plus 51 should be 92, right? So as you can see, the changes in enthalpy are the same. So this is something you will learn in your last week's content, which is all about Hess law. And then you should be able to find further information in your intro of this experiment. But what it is it doesn't matter whether you take reaction in one step or two separate steps, or changes in reaction enthalpy will be the same, right? So in our case of A and B, we took the two-step reaction, and in C, we took one-step reaction, right? So in the end, changes in enthalpy should be the same. And okay, so I think because I was putting some text, that's why it moved a bit downward. Okay, it doesn't change anything. Right. So compare the value obtained from the experiment with the value provided in page 3. So in your page 3, we do have in page 3 here, right? So we do have the value you're supposed to get based on the theory or based on under the ideal condition. So you're supposed to get about minus 44.5. For B, you're supposed to get about minus 56, and then for C, you're supposed to get about minus 100. But in your calculation or in your experiment, your value is with your heat from your reaction is a bit smaller than what you're supposed to get, right? Just let's assuming that minus negative is just convention, so this value is from your exothermic reaction, right? So obviously, heat from your reaction, which are in rest, is a little bit smaller than what you're supposed to get, right? And you will need to write a brief note based on the condition. Okay? So, okay, so I don't think we don't have enough information over here. So possible source of discrepancies in this experiment. Okay, so there's a hint over here. There we go. So in your table, you saw the temperature going up, right? At some stage, temperature is going down, right? From 36 degrees Celsius to 35 degrees Celsius. What it means is you are losing temperature. So for this experiment, using a thing called calorimeter, so it's basically it's a cup, and then you put a thermometer over here, and then you put your mixture A plus B, making C plus D. So in this type of experiment, your system, which over here, should be 100% isolated from surroundings. From surrounding. But when you look at the table from part A, temperature was going up and then maxed at about 36 degrees Celsius. But at some stage, you saw temperature going down to 35 degrees Celsius. What it means is, during the entire experiment, you are just keep losing some heat throughout the calorimeter, which doesn't provide 100% isolation. Because of that, your measured changes or your measured value is a little bit lower than what it's supposed to get, right? So based on the information over here, that is only thing you can describe, and I don't see any other problems because even B1 and B2 are the similar, and I don't see any irregular patterns except these values are a little bit smaller than what you're supposed to get, right? So the correct answer should be your calorimeter could not provide 100% isolation from the surroundings. So the temperature over here was about 25 degrees Celsius, right? And then the heat was generating. So if it provides 100% isolation, if you reach the Tmax, and it'll be 36 degree without any loss of heat. So it should keep the heat from your reaction indefinitely, but within say less than some seconds. I'm not sure how long it was, but you saw temperature dropping, which means you will keep losing some heat from your reaction. That is why your value from your experiment is a bit smaller than what you're supposed to get, right? Okay, so this is the end of your lab assignment, and you will just need to finish your assignment and then submit before your due date. And that's about it. And if you have any questions, please feel free to let me know. All right.